Up to now, we've focused on GPUs themselves, cores, memory, and clustering. But the moment you move from one GPU to many, a new component becomes critical: the network. When GPUs operate alone, networking barely matters. When GPUs work together in a cluster, networking becomes part of the compute path. If the network is slow, unreliable, or overloaded, GPUs, no matter how powerful, end up waiting. And waiting GPUs are wasted GPUs. This is why NVIDIA places such importance on networking in AI infrastructure, and why the exam tests it explicitly. Let's define networking in the context of GPU clusters. Networking means the movement of data between GPUs, either between GPUs in different machines, or between GPUs across a larger cluster. During training, GPUs must regularly share updated model parameters, synchronize their progress, coordinate computation. This communication happens many times per second, not occasionally. So when we talk about networking for GPU clusters, we are not talking about internet access, web traffic, user browsing. We are talking about high-speed, machine-to-machine communication that directly affects training speed. The first networking concept we need to define is bandwidth. Bandwidth refers to how much data can be transferred over the network in a given amount of time. A simple analogy is a water pipe. A wider pipe can move more water at once. A narrow pipe creates congestion. In GPU clusters, high bandwidth is important because large amounts of data are exchanged. Model updates can be very large. GPUs generate data faster than slow networks can carry. On the exam, when NVIDIA mentions large data transfers or high-volume communication, they are testing your understanding of bandwidth limits. Now, let's define the second critical concept: latency. Latency is the time it takes for data to travel from one point to another. Using the same pipe analogy, bandwidth is how much water flows. Latency is how long it takes for water to reach the destination. In GPU clusters, latency matters because GPUs must synchronize frequently. Even small delays add up when communication happens repeatedly. Low latency is especially important when GPUs exchange small messages frequently. Synchronization points occur often. On the exam, NVIDIA often contrasts bandwidth-heavy problems with latency-sensitive synchronization and expects you to recognize the difference. Here is a critical intuition that many beginners miss. GPUs are extremely fast. They can complete their calculations quickly, sometimes much faster than data can be moved across a slow network. When this happens, a GPU finishes its work. It waits for data from another GPU. It sits idle. From the outside, it looks like the GPUs aren't being fully used. But the real problem isn't compute, it's networking. On the exam, NVIDIA expects you to recognize that low GPU utilization in a cluster can be caused by network bottlenecks, not weak GPUs. Traditional enterprise networks were designed for file transfers, web traffic, general-purpose workloads. They were not designed for constant, high-speed GPU to GPU communication. In GPU clusters, traditional networking can introduce too much latency, too little bandwidth, unpredictable performance. This is why AI infrastructure often uses specialized networking technologies designed for high performance. You do not need to memorize specific technologies yet, just understand why normal networks struggle. As you add more GPUs to a cluster, something important happens. The amount of communication increases. Each GPU must send updates, receive updates, stay synchronized with others. If the network does not scale with the GPUs, performance gains flatten or even reverse. This is known as diminishing returns. This concept appears frequently in exam questions where more GPUs were added, but performance did not improve as expected. The correct answer usually involves network limitations. Exam traps. 1. Assuming slow performance means weak GPUs. Networking often causes the slowdown. 2. Confusing bandwidth and latency. They solve different problems. 3. Ignoring communication when scaling clusters. More GPUs mean more network traffic. 4. Believing networking is secondary in AI systems. Networking is part of the compute path. Let's lock this in clearly. GPU clusters rely on constant communication. Networking moves data between GPUs. Bandwidth controls how much data moves. Latency controls how fast data arrives. Poor networking wastes expensive GPUs. NVIDIA tests networking intuition, not terminology. If this lecture now feels intuitive, you are thinking like an AI infrastructure engineer, not just a learner.